In this video we are going to look at number 6. We're going to do A, then we're going to give you a chance to have a go at B. In A we see that in the denominator we've got Z bar, and we've already said that Z bar is not analytic, so that means the Cauchy's integral theorem is not going to be applicable here. So that means we just have to work this out manually, if you like. So we're integrating this along the circle centered at the origin radius 2. We've already seen how to parameterize that, so let's see how this works out. So number 6a, we have got integral from 2 to 2I of dz over z bar along the circle mod z equals to 2. So let's just do a sketch here. So this is the situation we have. We've got a circle of radius 2. We're integrating from 2 to 2I, and we are going in the counterclockwise direction. If I remember correctly, let's just confirm. Where are we? There you go. So counterclockwise direction. Alright, so that means we're going to be integrating from theta equals to 0 to theta equals to 90. So theta is 0 here, theta is 90 here. Again, this means z is 2 e to the I theta. We're going to need mod z bar 2 to the I theta. We're also going to need dz, which we've already seen. It's just going to be 2I e to the I theta d theta. Z bar is going to be 2e to the minus I theta. So the integral from 2 to 2I of dz over z bar is going to be 2I e to the I theta, 2I e to the I theta d theta. In the numerator is dz. In the denominator we've got 2e to the minus I theta, integrating from theta equals to 0 to theta equals to pi on 2. So strictly always in radian mode this time. The 2's cancel out, the e's combine to e to the 2I theta in the numerator, and then to integrate this we just divide by the derivative of this, which is 2I. So we're going to have I over 2I e to the 2I theta from 0 to pi over 2. So this is going to be 1 over 2 e to the 2I theta. If theta is pi on 2, it's just going to be pi I, and then e to the 0. Now e to the pi I is negative 1, so this thing is just going to be negative 1. It's negative 2 over 2. Alright, so we're now going to give you an opportunity to have a go at part B. You can pause the video, and then when you continue the video you can compare with our solution. In part B, you got the integral of dz over z squared around the circle of radius 1 centered at the origin. Right, so in this case we are looking at the integral of 1 over z squared, which is singular at the origin. Our contour is the unit circle around the origin. So that means this is not covered in Cauchy's integral theorem, because the region inside this contour is such that this function is not analytic, so we cannot say it is going to be 0. If there was no singularity here, then it's a closed contour, it's simple, then we can always conclude that the integral is going to be 0. So we do the integration manually again. Z is e to the I theta, dz is e to the I theta d theta. We're going to need z squared, it's going to be e to the 2I theta. We substitute, so that's going to be z squared, that's dz. We are going to do integral from 0 to 2 pi. We could do minus pi to pi, still going to work. The e's will cancel out to e to the negative I theta. Then we integrate, so that means we're going to divide by negative I. Then we do the limits. Now, so when theta is 2 pi, it's going to be e to the minus 2I pi, and theta is 0, is going to be e to the 0. But e to the 2I pi, negative 2I pi is 1. E to the 0 is 1, so this is giving us 0. So, but this is 0, not because the integrand is analytic. So this is just a classic case to demonstrate that the result of Cauchy's integral theorem is a one-way implication statement. Getting 0 here does not imply that the function that was integrated is analytic, even though the contour is closed. Okay.